Dear learners, greetings from IIT Guwahati. We are back to again this MOOCs course Fundamentals of Compressible Flow, module number 5. Title of this module is Expansion Waves and Oblique Shocks. Prior to this lecture, that is lecture number 3, we have discussed the following topics in lecture 1 and 2. So, those topics are expansion waves and in particular Frankel-Mayer expansion waves, its fundamental equations. Then it is followed by oblique shock waves, mathematical treatment of oblique shocks. There is a fundamental equation, we call this as theta beta m equations for oblique shocks, and we also discussed about oblique shock relations to calculate the flow property in a compressible flow domain. Now, in this particular lecture, we will again discussed some more details on the oblique shocks, and our main intention or attraction of this lecture is the graphical representation of oblique shocks, and through this graphical interpretation of oblique shocks, we can generate a curve what we commonly known as theta beta m curve, and this particular curve gives many fundamental inferences that are useful for supersonic and hypersonic velocities in which these bodies are flying. And apart from that, we will also see that how this theta beta m curve will be a useful way of graphical representations, and based on which we can get rid of the to remember this fundamental equation, that is theta beta m curve. Okay. So, let me start. So, the very basic background if I give to this oblique shocks, we can say that if a supersonic flow has to turn, then it has to encounter an oblique shock. Thus, an oblique shock is a natural occurring phenomena in which a supersonic flow can turn towards main bulk of flow through a flow deflection angle. If you look at this figure, the supersonic flow can turn towards itself through a flow deflection angle theta. And in a very special case, when this oblique shocks becomes a standing normal shocks in which the flow does not deflect at all. So, we say normal shock wave is a special case of oblique shock wave family in which streamlines are perpendicular to the shock waves. A strong oblique shock is typically considered as a normal shock, while the weakest possible oblique shock is a Mach wave. In today's class also we will prove it through this graphical representation. Normally the normal shock waves are straight and the direction of the flow before and after the shock, that means the shock wave is straight and the direction of the flow before and after the shock, we can say that before and after the shock the normal the flow streamline does not deflect and the streamlines are always straight. In same sense also oblique shocks are straight, but they are inclined to an angle to the upstream flow. So, this angle is always higher than the Mach angle and we call this as a shock wave angle. And in the last class we derived the fundamental relations and we call this as a theta beta m relations. So, what does it say? That when a supersonic flow has to undergo a deflection through an oblique shock, the flow deflection angle is considered as a vital parameter. So, a trigonometric relations can be obtained, and these the changes of oblique shock depends on two parameters, that is upstream Mach number and shock wave angle. Now, through this oblique shock relations we have tuned this oblique shock problem in such a way that we will as if solve it as a normal shock problem. So, how do you do it? We normally represent this oblique shock by decomposing this velocity vector in a tangential and perpendicular directions. only normal component of this velocity vector takes and if you consider, then this oblique shock problem can be tuned to a normal shock problem. And also you have seen that the tangential components do not contribute significantly for the property calculations. So, in that way the first relation that we get, we have to calculate the normal shock Mach number, that is m1 sin beta. Beta is nothing but your shock wave angle. And this normal, based on this normal shock Mach number, if you by using normal shock table, we can calculate other parameters like normal shock Mach number after the shock wave. Then also we can find density ratios based on the normal component of the Mach number, upstream Mach number. Similarly, for pressure ratio and temperature ratio, of course entropy. Okay. Now, we are going to discuss today the most important curve, what we call as a theta beta m curve. So, this theta beta m curve is nothing but the graphical representation of oblique shock relations. The famous equation that we land up in the oblique shock relation is tan theta is equal to twice cot beta whole bracket m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta plus 2. And if you see these equations, we have three major parameters. One is theta, other is beta, third one is m. Now, what does this mean? Theta is your flow deflection angle, m1 is upstream Mach number and beta is the shock wave angle. Now, since it is a mathematical relations, we can use these relations for variety of Mach numbers or different Mach numbers starting from Mach 1, Mach 2, Mach 3 likewise. And similarly, for each Mach number we can play with the theta. So, in such way, if you can do that, we can generate an array of plots. So, if you see this particular figure, the y axis represents the shock wave angle, that is beta, that is in degree, and x axis represent the flow deflection angle theta, which is in degree. And in these things there are different graphs has been plotted. You can see these graphs represent graph A, B, C, D, E, F, they are representing Mach 2, Mach 2.5, 3, 4, 5 and 8. So, that means you can also generate an array of curve. Okay. Now, if you look at some characteristics features of this array of curve, what you can say that there are I can divide this in two major category is that if you look at this particular one particular Mach number, let us say this first case curve A Mach 2. So, this is drawn for different theta, different flow deflection angle, and if you see that there is one particular point we cannot extend, that means maybe something like 22 or 23 degree beyond this, there is no further solution of flow deflection angle is I mean there is no oblique shock solution if you go beyond this flow deflection angle, because there is no solution on this curve. So, that is one category. So, this point refers to a location where we say A2. So, A2 is a location which is called as maximum flow deflection angle, beyond which oblique shock solution is not possible. So, this is at one particular Mach number of 2. Now, similar points can be located for other Mach numbers like B2 for Mach 2.5, C2 for Mach 3, D2 for Mach 4, E2 for Mach 5 and F2 for Mach 8. So, these curves can be plotted. This is first category. Second category points can be denoted as A1, A2, A3. So, if you look at these things that if you talk about the downstream Mach number, that is M2, M2 becomes subsonic at one particular point or solution point. So, that point in this curve, if we can denote, that is that point refers to A1, B1, C1, D1, E1 and F1. So, these points you can denote that this. So, if you plot all such of array, we will have another set of array that joins A2, B2, C2, D2, E2, F2. One sets of array we can draw it for A1, A2, A1, B1, C1, D1, E1, F1. And if you look at, there is a difference, and this difference keeps on reducing if you increase this theta, increase theta, and if you increase the Mach number. So, as if you go higher Mach number and higher flow deflection angle, the point F1 and F2 are very close, but if you go to lower Mach numbers, this gap is a reasonable gap. That means, we have a distinct points. So, these are the some of the characteristics features of this curve. Now, we will go back one by one and try to find out what are this significance. So, first inference that we are going to draw from this theta beta m curve, that for a given upstream Mach number, that is m1. So, for a given upstream Mach number m1, there exists a maximum flow deflection angle. So, this for example, for Mach 2, the maximum flow deflection angle is A2. For Mach 2.5, the maximum flow deflection angle is B2. Likewise, for Mach 8, maximum flow deflection angle is F2. Now, the physical geometry, now this is what the curve tells us, but if your physical geometry, if your body or some kind of geometry that has such a shape that it has a flow deflection angle higher than this value, that means, for this Mach number, let us say Mach number of 2.5, approximately theta value is 30 degree. If this supersonic flow at Mach 2.5 encounters a wedge or a body which has flow deflection angle higher than this 30 degree, then we say that it has encountered a flow deflection angle of the geometry which is maximum that was supposed to be for an oblique circle solution. So, that means, here if you look at this particular figure, we have a wedge shaped body, it has an angle theta which is greater than the theta max. So, I will say this represents the theta max. Now, this theta max, if your actual angle is higher than this theta max, then what is going to happen? So, we will find that there is no oblique circle solution possible. Then what is going to, then how this flow is going to adjust. So, for that reason, there will be shock wave which is supposed to be formed for this body, it will be no longer attached. So, this particular thing we call this as a detached shocks. So, in such cases, the shock wave will be a curved one. So, it is a detached shock, and in our gas dynamics terminology, we call this as a bow shock. So, this detached shock takes the shape of a bow and arrow. So, it is called this as a bow shock, and this bow shock is a very common phenomena when there is a supersonic flow past blunt bodies. Okay. Now, what will happen if the flow deflection angle is less than the theta max? So, this bow shock which was supposed to be detached, now we will have a oblique shock solution. So, it will remain attached to the body. So, the physical geometry has a angle which can turn the flow by an angle theta, and its value is less than the theta max. So, the flow can turn and the shock will remain attached. So, for this kind of geometry or wedge shaped body, when the supersonic flow encounters, so through an oblique circle, the flow is going to be turned. That means, streamline will turn through an attached shock, and this is a very common process that we call this as a M2. So, we call this as a natural occurring process of, that means, a weak oblique shock is formed. And for this case, there are two solutions for oblique shock wave angle for a given upstream Mach number and flow deflection angle. So, what happens? Let us say that we are looking at Mach 2. So, upper limit is theta max, for which the theta max is A2, and we are looking for a solution theta less than theta max. So, basically we are in this dome and we are in this Mach number. So, any flow deflection angle, it will cut this curve at 2 points. Okay. Now, we were looking at m1 is equal to 2. So, it will cut at 2 points. So, these 2 points are normally we call this as a shock wave angle. That means, there are two solutions possible for a given flow deflection angle. Now, how do you find out which one we should take? So, for an attached shock solution, there are two solutions of shock wave angle for given upstream Mach number and flow deflection angle. Now, one refers to strong shock, that is higher shock wave angle, other refers to weak shock, that is lower shock wave angle. So, same, let us say we are looking at something about 17 or 18 degree. So, this particular line cuts this Mach 2 curve at two locations, and from this we can drop a vertical, and there are 2 points it will cut, one could be about 82 degree, other could be about 42 degree. So, it means for about flow deflection angle 13 degree, the and supersonic Mach number at 2, we have two possible solutions of shock wave angle, one could be 42 degree, other could be 82 degree. So, this means 42 degree refers, that means lower value refers to a weak shock solutions, and 82 degree refers to a solution of higher shock wave angle. And now, which one you should see? Now, if you look at this particular figure here, that for a given theta, if you for a physical geometry for a given theta, we have one value of say beta lower value, we have beta higher value. So, that means for m1 over 2, beta lower value will be 42, and for same Mach number the beta higher angle will be 82 degree. So, we have a strong shock solution or weak shock solution, but in our all gas dynamic problem, always weak shock is preferred, because weak shock is normally encountered as a natural occurring phenomena, whereas strong shocks is normally viewed through a mechanism which is called as a back pressure, controlling of back pressure through independent mechanism. So, we will, because this is not a solution of higher strong shock is not occurs in a natural process. So, it is a very basically controlled process in which we can generate a strong shock, but a natural occurring process is a weak shock solution. So, it is always favored. Okay. Now, moving further, for an attached shock situation, the oblique shock is always straight and attached to the body. As you can see here, streamlines are parallel both in upstream direction and the downstream directions. So, downstream direction the streamlines are makes an angle theta, and it is parallel to this inclined surface. The Mach number after the weak shock is always a subsonic. So, that means, if you for an attached shock situation, when you say M2 and it is a weak shock solution, so Mach number is always less than M1. Okay. This is what for a weak shock situation, but if you take a strong shock, your M2 will be subsonic. So, for example, as I mentioned that for an flow deflection angle of about 13 degree. We have two solutions, one is weak, for which we say beta lower value, and for higher value we say beta h higher. Now, if I choose my solution, beta lower value is 42 degree, and we have m1 is already you have taken 2, and if your solution is and theta 13 degree and your solution is 42 degree, then we have m2 which is this, which will be less than m1. This is the first conclusion. Now, if for this condition, if my solution is, if I take beta higher value of this, that means strong shock solution 82 degree. So, this will say, this will give me a solution m2 which is less than 1. So, here it is subsonic, that means downstream value Mach number is always subsonic, that is the reason it is a strong shock. But in a weak shock solution, downstream Mach number is still supersonic, but it is lower than the upstream Mach number. Next inference we can say is a very fundamental things that we have been talking about: Mach wave, oblique shock and strong shock, these three things. But actually the proof comes here, that we always say that Mach wave when they merges, it is a initiation of oblique shock, and oblique shock when it becomes stronger, it becomes a normal shock. But what is the physical background of it? So, for that reason we are going to refer in these inferences that when there is a 0 flow deflection angle, that means there is no deflection angle, the strong shock takes the shape of a normal shock. We call this as a shock wave angle with significant pressure difference between upstream and downstream. So, as I say that when the oblique shock becomes strong normal shock, that means when you go for the strong shock solution, then it has a 0 deflection angle. Now, now let us see that in this particular curve what is the 0 deflection angle mean to us. Now, if you say that for irrespective of what Mach number you take, when you take a flow deflection angle, whether you take Mach 2, that is for curve A, or Mach 8 for curve F, you will find that 0 deflection angle refers to mainly y axis, that is shock wave angle. And this particular things that for this for each curve, the upper limit is 90 degree, that is beta is 90 degree, okay, and all the Mach numbers curves merges at beta 90 degree, but their starting points are different. Like curve m1 is equal to 2 starts with maybe beta is equal to 30 degree, but merges at 90 degree. Similarly, curve f that starts with something about beta is equal to 8 degree, but merges still at 90 degree. So, that means each curve cuts this y axis, that is shock wave angle, at two locations, one at 90, always at 90 degree, and we strongly say that this is a normal shock, because that refers to a value beta is equal to pi by 2, okay, and this particular things refers to this. Now, the lower limit is different for different Mach numbers, and in fact we have been saying that that is nothing but your Mach angle. So, these lower limits, they refer to Mach angle, and each Mach angle is, we can, if you know the Mach number for Mach 2, the Mach angle would be 30 degree, that we can find out from here. So, mu m is nothing but 30 degree and mu m is equal to beta. So, it is a Mach wave. So, the weak shock solutions or for 0 degree deflection angle is nothing but a Mach wave, and 90 degree refers to a strong shock. Now, if you look at this particular figure is theta, which is actually this theta goes to 0. When theta goes to 0, we can draw a Mach wave that can start here. This Mach wave this Mach wave and this weak shock, they coincide, and this strong shock will become normal when beta is equal to 90 degree. That means, this strong shock becomes normal shock. So, this is the physical interpretation of this zero flow deflection angle. So, weak oblique shock becomes a Mach wave when the shock wave angle equals to the Mach angle with in very small pressure difference. Next inference is that, let us see that for a given flow deflection angle, that means, for a given flow deflection angle, when you say fix a theta, as the free stream Mach number decreases from higher to low supersonic value. That means, when you are for a given flow deflection angle, let us say I am 30 degree, 10 degree I am going for a flow deflection angle, and I am moving from the free stream Mach number decreases from high to low. That means, I am going in these directions. So, that means, I am going from Mach 8 to 2, that means, in the decreasing directions. What happens? The shock wave angle increases for weak shock solution. That means, this shock wave angle, if you drop normal for each case, the shock wave angle decreases, and this is for weak shock region, weak shock solution. Of course, why I am saying weak shock? Because weak shock is a natural occurring process, and we do not normally go for strong shock solutions. Now, for a fixed deflection angle, there is a Mach number below which no solution is possible. It refers to a maximum flow deflection angle at that Mach number. That means, for each Mach number, these points A2, B2, C2, D2, E2 and F2, they are fixed point, and beyond this, that means, for this case, beyond this value there is no oblique shock solution possible. Beyond B1, there is no oblique shock solution possible for Mach 2.5. For beyond Mach 8, that means, beyond about 43 degree, there is no oblique shock possible for Mach 8. So, this is what it means. And if it is, and when it is theta is less than theta max, we get an attached shock, and when you say there is no oblique shock solution is possible, shock wave will remain detached. So, we call this as a bow shock. Okay. And so, from this analogy, what we can conclude that we can make an mechanism that or we can say that oblique shock is a physical mechanism or natural occurring mechanism in which we can turn the flow as per our wish just by controlling few parameters. What are the parameters? One is upstream Mach number, other is the flow deflection angle, and all of them we call this as a controlling parameters. So, what does this mean? That when the normal component of Mach number ahead of the shock increases, the strength of the shock wave is always increased. That means, when this Mn1 increases, the strength of the shock wave also increases. To increase this Mn1, we have to either increase M1 or we have to either increase beta. But increasing M1 is one sense that we can increase the upstream flow Mach number. But to increase this beta is again a function of theta and M1. So, this either we can go through increase in the theta angle or through the combination of M1 and theta we can change this angle. So, that way we can say that whether we can go for a weak shock or strong shock. So, this is what it means, that normal component of the Mach number can be increased by increasing the shock wave angle or through higher flow deflection angle. The other possibilities of increasing the normal shock Mach number can be achieved by increasing the upstream flow Mach number. So, as a rule of thumb, when the flow deflection angle increases, keeping upstream Mach number constant, the shock wave angle increases. And similar way, when the, as a rule of thumb, when upstream Mach number increases, keeping flow deflection angle constant, the shock wave angle decreases. And how this conclusion we made will solve some problem and to get the feel of it. Okay. Now, with this I will give a complete picture that till now what we have covered. We have covered the oblique shock relations, and today also we represent that oblique shock relations in a graphical form. We call this as the theta beta m curve, and we say that by doing so what we have achieved is that we have tuned this oblique shock problem to a normal shock, where it is very easy for us to refer the normal shock table. So, what it means is that a given problem, first you given oblique shock problem, first you change it to a normal shock problem. How do you do that? By calculating in the normal shock Mach number Mn1. This, for this m normal shock Mach number, we can use this normal shock table, and this table we can refer in, mainly we will be referring this particular book, John D. Anderson, Modern Compressible Flow. In this table what you see is that for a given Mach number we have pressure ratios across static pressure ratio, static density ratio, static temperature ratio, stagnation pressure ratio. Again there is another parameter, stagnation pressure to static pressure ratio, and of course the Mach number downstream or after the shock. This is how we are going to do. Now, for a given oblique shock problem, we have to refer this normal shock table, but prior to that we have to use this graph. Now, in our earlier situations there are two ways of using this graph. Either you can use a trial and error approach to solve a problem to find theta beta m relations, or instead of to get rid of this problem, then you can directly refer this graph and find the values or obtain the values for shock wave angle. So, this is how the philosophy of graph or advantage of graphical representation. Now, with this background we will try to solve some numerical problems. Now, our main intention of this numerical shock problems is that how you are going to use these graphs. So, in my last lecture also I solved this particular problem, but in a different context, that by using trial and error approach, by solving that theta beta m relations, I have demonstrated that how we are going to use without the use of graph. But here we are using the same problem, but using these graphs and this normal shock table. So, for this kind of problem, the first thing that you must do is that draw the physical aspects of this flow problem. Okay. So, here the question was given that a supersonic stream at Mach 3, static pressure, temperatures they are given. So, these are the upstream conditions which are given to us. So, it is deflected through a compression corner. When there is a compression corner and here the angle is 20 degree, then there will be an oblique shock formation. So, that means we have to see that for this kind of Mach number and theta, whether we will find an attached shock solution or not. So, for that we first draw the physical problem. So, this theta is 20 degree and it is a compression corner. So, there will be an oblique shock. This angle we call this as a beta, which you do not know, but what happens to the streamlines? The upstream streamline is at Mach 1, Mach 3, M1 is 3, pressure is 90 kPa, temperature is 290 Kelvin. Now, after this oblique shock the flow turns. So, we have M2, P2, T2, but the question that was asked we will have to find out stagnation properties as well. So, here I can write P naught 1, T naught 1 and here downstream P naught 2, T naught 2. So, these are unknown quantities and this P naught and T naught 1 is a function of M 1. So, to solve the problem, first thing what we are going to refer is that refer this theta beta m curve. So, to refer this theta beta m curve, what you require, your M 1 is 3 and your theta in this case we say 20 degree. So, for theta 20 degree and M 1 is 3. So, here the curve M 1 of 3 could be noticed something between B is 2.5, C, curve C we can go for. So, this curve C refers to M 1 is equal to 3. Now, this for this particular curve and for theta is equal to 20 degree, we can locate this point. Okay. So, this approximate value of beta we can obtain as, so it is something about close to 37 degree I can assume. So, beta value can be assumed or we can roughly say that this will be around 37 degree. Once we have this, then we know beta. So, once you know beta, remember that we in this step we have got rid of theta beta m relations. That means, we are not using any trial and error approach, rather solving this problem graphically using this graph. So, when you say beta is this, m 1 this, then we can tune this oblique shock problem to a normal shock problem. So, then in that case you have to calculate what is m n 1, that is m 1 sin beta, and we all know m 1 3, beta is 37 degree. So, it will be about 1.82. So, normal shock Mach number is 1.82. So, that then you have to refer this normal shock table. So, this is an extract from the book and John D. and Russell. So, for this normal shock table, if you refer for m n 1, so here m 1 now refers to m n 1. So, this we have to say that for 1.82 we have to note down these values. So, note down this value means we have to calculate P 2 by P 1. So, P 2 by P 1 will be 3.698, T 2 by T 1 is 1.547, P naught 2 by P naught 1 0.8038 and M 2 is 0.6121. Fine. And we all know this, of course, we require stagnation. So, for the stagnation condition you have to refer this relation P naught 1 by P 1 is equal to 1 plus gamma minus 1 by 2 m 1 square to the power gamma by gamma minus 1, T naught 1 by T 1 is equal to 1 plus gamma minus 1 by 2 m 1 square. So, we have m 1 and we have gamma 1.4. So, from this we can calculate this P naught 1 by P 1 is 6.73 and T naught 1 by T 1 is 2.8. So, that we can get P naught 1 is P 1 times this, P 1 is 90. So, P naught 1 would be 3305.7 kilopascal and T naught 1 would be 812 Kelvin. Okay. So, once you know this P naught 1 T naught 1, use these relations, then we can obtain the values of P 2 as 332.8 kPa, T 2 448.6 kPa, P02 2657 kilopascal, T02 do not change. Then what else remaining? M2. So, for M2 we require Mn2. Mn2 already noted down, that is Mn2 divided by sin beta minus theta. So, this value would be 0.6121 divided by sin beta minus theta means 37 minus 20, that is 17 degree. So, M2 would be 2.04. Okay. So, this is how you are going to solve the problem. Now, next question is that here you have to give an emphasis what is the effect of Mach number and flow deflection angle. So, for the same data referring to the question 1, that means same M1, the flow deflection angle is now increased to 30 degree. So, when the flow deflection angle now theta goes to, for same problem the theta goes to 30 degree. When the theta goes to 30 degree, and that means your main problem now changes, M1 is 3, theta becomes 30 degree. So, for same M1, that is curve C, when theta becomes 30 degree, so this will tell you that this will give you beta is will be equal to 52 degree. So, Mn2 will now become M1 sin beta. So, this will be 2.36. So, once you have Mn2, then you refer normal shock table. For 2.36, 2.36 will be somewhere in this region. So, you can note down these approximate values, that P2 by P1 is 6.28, T2 by T1 is 1.993, and P02 by P01 will be 0.5615, and for this Mn1 we will have M2.5286. Okay. So, this we get from the normal shock table. So, prior to data from the question 1, we have already this data, P1 90 kilopascal, P01 3305.7 kilopascal, T1 290 Kelvin, T01 812 Kelvin, and this refers to M1 is equal to 3. Now, using this data we can now find out what are the values. P2 is equal to 565.2 Kelvin, T2 would be 578 Kelvin, P02 would be 1856 Kelvin, and T02 remains same, and Mn2 would be M2 Mn2 by sin beta minus theta. So, beta minus theta is now 52 minus 30, 22 degree. So, this will give you value M2 1.41. So, what happens if you make comparison? So, your the shock wave becomes stronger, because the static pressure is drops. In earlier case this P naught 1 was in this case the P naught 1 is 1856 kPa, and in earlier case this P naught 2 was 2657 kPa, that is with respect to question 1. Okay. So, with respect to this the static pressure stagnation pressure drops to a large value. So, this stroke becomes stronger, static pressure also higher than the previous one. So, the shock wave is so it is a strong becomes stronger. Okay. P2, T2 they increase and P naught 2 again drops. So, the shock wave becomes stronger. So, it means that for a given flow deflection angle for a given Mach number, if the flow deflection angle increases, the shock wave becomes stronger. So, this is proved with this data. And the next problem what says that for same data referring to the question 1, now here deflection angle remains same, but the shock Mach number is increased to 5. So, referring to that data from the question 1, we can say we have same P1 90 kilopascal, T1 290 Kelvin, P naught 1 3305.7, T naught 1 812 Kelvin. So, this refers to M1 is equal to 3. Now, this M1 becomes 5, theta remains same. So, when M1 becomes 5, we have to refer theta is 20 degree and M1 refers to 5 means cor B. So, this particular location will give you beta above is 30 degree. When beta is 30 degree, we can find out Mn1 M1 sin beta. So, this is 2.5. So, for this Mn1 2.5, we refer this normal shock table for this Mn1. So, this will give you these ratios P2 by P1 7.125, T2 by T1 2.187, P naught 2 by P naught 1 0.4793 and Mn2 0.513. Okay. Now, with this data, initial data for P1 and T1 and with M1 5, then we can calculate P2 as 641.25 kilopascal and T2 is 620 Kelvin, P naught 2 1649.5 kilopascal, T naught 2 remains same 812 Kelvin. So, this from this we can also calculate M2. M2 is Mn2 sin beta minus theta. So, M2 will be 2.95. So, if you can see that M2 is little bit higher, but at the cost of the decrease in the shock wave angle. Shock wave angle now from 52 it now reduces to 30 degree. Okay. So, but at any case when the M1 increases, so that means shock wave becomes stronger. And this can be proved that if you will see here P naught 2 is still lower 1650 Kelvin, that means static pressure stagnation pressure drops to a large value. Okay. So, that means static pressure drops close to by half, stagnation pressure drops close to by half and static pressure rises about 6 times, that means P 2 is about more than 6 times than P 1. So, this when N 1 increases, shock wave becomes stronger for fixed deflection angle. Okay. P naught 2 drops, P 2 T 2 increases. Okay. So, this gives a quantitative estimation that how by controlling the parameters of Mach number and theta we can control the oblique shock properties. Okay. With this I come to the end of this oblique shock. Thank you for your attention.